let's start. Can I borrow your book, please? Let's see. Right, so we're continuing with our integration. And to start with, I have to tell you, I have to turn this on. By substitution we did simple rational functions. Okay. Hold on, just give it a second. You can do it. Come on. Yeah. Alright, does anybody know what a rational function is? Reasonable. A non-crazy function. No. Did you lose your glasses? Did you take them, Monica?
Yeah, obviously.
Oh, give it back to him, Monica. Did you take them? Jerry, where did you put them?
I don't know.
It's like a class of children. Can you see if you don't have your glasses?
Of course I can't see.
Did you take them, Monica?
Yeah.
Okay. Can you give them to him, please? Thank you. Right, now we can continue. So, a rational function simply is a function which is a fraction, and on the top we have something called a polynomial. A polynomial is just something like a linear, a quadratic, or a cubic. And on the bottom we have something which is also a polynomial, which can be a linear, a quadratic, or a cubic. So an example of a rational function would be this: minus 10x minus 7 over minus 5x squared minus 7x minus 8. This is a rational function. Reasonable. Got that? Continue. So what we want to learn in this lesson is how do we integrate these rational functions. So there's actually a couple of different ways depending on the type of problem. So we'll actually, let's actually do this one first as an example. So what is special about this type of problem? Well, on the top is a linear, and on the bottom is a quadratic. But what's very special about this is there's actually a relationship between the top and the bottom. Can anyone see what that relationship is between the top and the bottom? There is a relationship.
Double. Numbers. Negative. Nothing. I'm serious.
Do you know in those anime cartoons where the character sighs and a little bit of air comes out their mouth? Do you know that's the animation I want right now. Sort of. Not this. Anything else? It's not double because that's it. Yeah. That if you look at the bottom and get its derivative, you'll see you'll actually get the top line. Now that's important. If that happens, the way to deal with this problem is with a substitution. You would say let u equals minus 5x squared minus 7x minus 8.
Yeah.
So that means du dx would equal minus 10x minus 7, which then means dx equals du over minus 10x minus 7. Putting these two back in, we now get integrate minus 10x minus 7 over u du over minus 10x minus 7.
Yeah.
Cancel, cancel. Integrating 1 over u, log u plus c. So the answer is log that plus c.
If we cannot divide by derivative.
Yeah, well, this is what the whole chapter is going to be about. What do we do in different situations? So, if is going to come up in example number 3 and 4. Okay, write this one down. This is our first one. Did you write that down, Christy? Yeah. Continue? Yeah. Okay, next example now. So the good news is for our next example is when we have something like this. And this is a linear and a linear. And for these, the good news is there doesn't need to be a relationship. If they're both linear, then the following method would work. In fact, another substitution. Yeah. So we get then du dx equals 9. So then we get dx equals du over 9.
Yeah.
But later it will be useful to have, okay, so before I continue with that sentence, at the moment we have u in terms of x. It will be useful for later to have x in terms of u. So just rearranging this, I can say also that x must equal, let me see, u minus 7 over 9. Now, that will be useful in a moment, you'll see. So this question becomes integrate 9x minus 2 over u du over 9. Now this is kind of like your point, KJ. We do not have a cancel in here. We do not. Yeah, but if we just simply put the x in here, then we get this. I'll take this 9 out. 1 over 9, integrate 9, u minus 7 over 9, minus 2 over u, du. Now that's nice because they cancel. So that's u minus 7 minus 2.
U minus 9.
Yeah, u minus 9 over u, du. Which is 1 over 9, u over u,
1.
and 9 over u. So now, this becomes 1 over 9 u minus 9 log u plus c. So that becomes 1 over 9, 9x, I don't care about the 7, minus 9 log 9x plus 7 plus c. Or in other words, final answer is x, minus 9 log 9x plus 7 plus c. That's the answer. Okay, so write this example down.
So why 1 over 9 multiplied 9?
1 over 9.
Look now.
Here. 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 Here.
Yeah.
Ah, you.
9 plus 7.
Is 9x plus 7. And I wrote 9x. I know what I did. Why don't I care about the 7? It's in the C. Because this would have just been plus, whatever, 9 over 7.
Can I write though?
Yes. Yes, you can.
To prevent.
No, that's fine. That's fine. The solution looks a little bit nicer here because I can just have the C absorb the constant. This is a usual thing to do in these types of situations. What roll did you get? Breakfast roll?
Yeah.
Delicious, huh? My favourite with brown sauce. You know brown sauce? Yeah. Traditional Irish breakfast on a roll. Tasty. See, I only had porridge for breakfast, and I'm thinking something extra should have nice. A few sausages, maybe. Okay. Got that? Yeah. Continue. Sean?
Yes.
Can I continue?
Yes.
Okay. Yep. Right, now it's starting to get a bit harder. So, just before we continue, if I just remind you of a question that you had a few lessons ago. In the implicit derivative, page 8, question 12D. I asked you for the derivative of sine inverse x. That's it there, Andrew. Now, if you did it, you will have the answer, but if not, I'll do it now. But does anyone remember the trick here for getting the derivative, yeah? Yeah, apply sine to both sides. Implicit derivative. So then dy dx equals 1 over cos y, which is 1 over cos sine inverse x over 1. And then by drawing our triangle, x1 and root 1 minus x squared. Is that right?
Yeah.
Cos is that over that. So this becomes just 1 over root 1 minus x squared. That's the derivative of sine inverse. So then logically, if the derivative of sine inverse is this, then the integration of this is sine inverse. So therefore, we can have this rule, that to integrate 1 over root 1 minus x squared dx, that's equal to sine inverse x plus c. You'll also notice that I think I asked you for tan as well, maybe? Yeah, I asked you for tan as well. Yeah. I asked you for sine, cos and tan. So in a similar manner, you can get this result by using tan. In question part, whatever the tan one was. 1 over 1 plus x squared dx, that integrates the tan inverse x plus c. So in other words, these two formulas will be useful for the integration chapter, and you should make note of them. Likewise, oh, and by the way, I have seen them in semester 2. The only proofs on the exams are proofs involving trigonometry. So in semester 1 you have no proofs. In semester 2 you do have proofs, but only in the topic of trigonometry. So technically these count as things that you may need to prove in the exam, and they have asked you to prove them on the exam in the past. So these are proofs which are on the exam. Should we say exam proofs? Yeah. In other words, if the thing has a sine or a cos in it, it's something they could ask you to prove. That's basically the rule I'm saying for proofs in the exam. And this came up in section A, so you had no choice but to do it. Okay? Continue.
Have to memorize it.
Well, it's not, it's the technique that you need to remember. It's using sort of implicit differentiation.
So we have to start with y equals
Yeah.
inverse x.
Start with this to get to this. Yeah. Yeah?
I mean, what is the
One
question?
sec, yeah.
No, you.
Go ahead, yeah.
What is the question? Just give us like this, like integrate 1 over square root of 1.
Oh, if they just gave you that, then this result is in the formula book, so you can, you know.
Oh, okay.
But they sometimes have asked you to show or prove this result, so that's different. But now, if they simply asked, we can just give the answer.
How can 1 and x and just 1 minus x together?
Huh? How do we get this?
Yeah.
Because the definition of sine is opposite over hypotenuse.
Oh.
Yeah.
We can't just use like sine together equals 1 together equals 1 and divide square root.
Interesting.
This becomes easier.
I suppose for this case, yes, you could. But I don't know if you could do that in the tan one.
I could do that.
You think so? I see what you're saying. So like here, you would end up saying cos squared y plus sine squared y equals 1. So then we wanted cos. So cos y equals square root 1 minus sine squared y. But sine y is x. So 1, yeah. It works. Although I suppose technically, because you're doing it this way, you do have an issue of choosing between plus and minus because you took a square root.
Oh, we know from graph and from your perspective, here is almost like 100 plus sine, all of them are plus and something like that.
Yeah, but you would have to give a reason for choosing plus instead of minus. You're right, it is plus. I know it's plus because that's what I got. And that's what it is. But if you're doing it this way, then you're going to have to justify why you chose plus. Continue. I'm not saying, KJ, I'm not saying it's wrong. I'm just saying it might not be as quick as you think because now you have to say why you chose plus. Okay, so now we've done that, let's go back to the integration. So the next example I want to look at is something like this. Let me change this a little bit, let's make that a 9. And let's make the top a different number. Let's make that a 16. Okay, so this one, on the top we have a linear, and on the bottom we have what? A quadratic, although it's kind of a special type of quadratic. What's unusual about this quadratic?
No B.
There's what? No x, only an x squared.
Derivative of derivative.
No, that's true. That's true, Jerry. But
No.
not the relationship. Not the relationship. The relationship is just that this is linear, and this is a quadratic. But it's actually called a depressed quadratic. Depressed quadratic means it's missing its x. It has only an x squared. Huh? Oh, I suppose if you want it's a constant, not a linear, really. I mean, it depends on your use of language here. It's linear in that on the graph it would form a straight line, although the straight line is horizontal. So We'll say it's a constant then. Be a little bit better. Okay. No, that's fair enough. Right. So this kind of looks like this. Kind of looks like this, doesn't it? Although it's not quite that. What's the problem? Well, we have a 16, a 4, and a 9, whereas my rule is a 1, a 1, and a 1. So we need a way to simplify, and this is with a substitution. But this is how the substitution works here. You let u equal to the square root of the first piece over the second piece. So this would then become 2x over 3, or in other words, 2 over 3x. If you use that substitution, what do you get? You get du dx equals 2 over 3. So then dx would equal 3 over 2 du. Yeah? And also, I know it might be useful later, maybe I'll just want to also say that x equals 3 over 2 u. Okay, so let's see what I get. Integrate 16. Now, this is not u, is it? Because u is 2 over 3x. So I'll just have to replace the x now for 3 over 2u squared plus 9, and then dx is 3 over 2 du. Now something very nice happens here. This becomes integrate. 3 over 2 times 16 is 24, isn't it? Yeah. 24.
Right.
Yeah. Now this becomes 9 over 4. But the 4 cancels this 4, so it just becomes 9u squared plus 9 du. So this is nice because now I can take out the 24 and the 9, leaving me with 1 over 1 plus u squared du. Perfect, because now this is the tan inverse of u. And u we said was, where's it gone? 2 over 3x. And that's that one.
How to find a u?
Yeah, it's like this, Sean. You let u equal to the square root of the first over the second.
Why?
Why? Because if you do that on this line, you will always get the same number here and here, which lets you pull it out. That's the reason. Choosing this substitution will make this line have the same number here.
So it should only this one is applied in depressed quadratic.
Yeah, because that's the reason is because this trick requires you to have 2 pieces. So then you might ask, well, what do you do if you have 3 pieces? And that is next. Yeah?
Is this the hardest in whole chapter?
Not even close. I'm sorry, if you think this is hard, you're going to be in for a shock. Look at P. That's the hardest one. And it takes about 20 minutes. And it's usually a section B question.
Oh, really?
But it's usually one section B question. Like it's a whole section B question. That's that.
Which one? So
No, I won't tell you yet. You might have nightmares. Right. Next example?
Yes.
Yep.
Teacher,
What?
why the last part? Why is that
Oh, Jerry, my heart. This row.
No.
Hmm.
It's
Tan inverse. This becomes this.
Yeah, where is that? 2 or 3.
Ah, because it's U, and U is this. It was tan inverse U, and this is U.
Oh.
Yeah? Cool? Okay, next example. Integrate a constant over a quadratic. 17. Right, now, our technique we used in the last example will not work. Why not? Yeah, so what can we do? No. No. No, no, no. The technique previously would work here, except we need to do something to make it work. Because right now we have 3 pieces in the denominator, but we need only 2 pieces. Yes! What's this called, Jerry?
I don't know that.
You do know what this is called. Nobody say it except Jerry. We'll all wait for Jerry to give its name. Go for it, Jerry. No, Jerry, don't look at anyone. Tell me.
I don't know that. I don't know.
Try. No, try. Don't say it. Don't you say it. Jerry's going to say it. What is it, Jerry? So? No. Ah, come on. You come on. You should know the name of this. What's it called? Good try. Oh, think hard. Come on. I know dictionary. Completing the square. Completing the square. So, here we need to complete the square. We got 16 over x minus 4 squared plus 1 dx. Now we can use our trick. We can say u equals the square root of x minus 4 squared over 1, which will equal x minus 4. So if u equals x minus 4, what does x equal? U plus 4. And also, what does du dx equal? 1. So dx equals du. Yeah? So putting these 3 together, we can get integrate 16 over u plus 4 minus 4 squared plus 1 du, because I've replaced the x with u plus 4. And now that's going to make this happen. 16 over u squared plus 1. Now it's a lot nicer, isn't it? So now it's just going to be 16 integrate 1 over 1 plus u squared du, which is 16 tan inverse u plus c, which is 16 tan inverse x minus 4 plus c. Yeah? What's wrong? Oh, spam. Yes?
Can we just step 2?
Yeah.
If the top is 16, so we put it in.
Oh, yeah, you can do it at the start, yeah.
And the bottom is 1 plus x squared.
Yeah. 1 plus u squared.
So we can just get the
Just get the answer.
because
Here you said take out the 16, yeah?
that
And then on the bottom,
1 plus
u squared.
x minus 4 squared.
X minus 4 squared plus 1.
We can see the x with x minus 4 squared
Is the u.
is u.
Yeah, but then it gets a little bit confusing if there was like a number here.
1 is 1.
No, it won't always be 1. Sometimes, for example, here, you get a number. In this example, I got a 1 here only because this was a 1. But this could have been like a 4. So, you're trying to take a shortcut. Bit dangerous. We should do it this way. Because here it was nice because this was a 1. But if it wasn't a 1, if this was a 4, then this would be a 4 here. And this would be a 2 here. And then this would be a half. You know, and that could happen. Did you write this down? You got that? Yeah? Okay, so can you try these for a couple of minutes? These are all standard integrations on the exam. And my experience is, for these ones, they don't often tell you what to use for the u. So just to recap, you really have just 2 choices. Either you make u equal to the denominator, or u equals root the first over the second. One of these should simplify your integration. Okay, try these for a few minutes.
What is denominator?
Huh? Denominator?
Yeah.